So the title of our handout is Excellent Exponents. Today we're going to be looking at exponents and some rules of those exponents. So before we can look at rules of exponents, we got to know what is an exponent. So at the top of our paper it says here that a blank is a small superscript number that shows how many times a symbol or a number is multiplied. And you guess what word's going to go in there? Exponent. All right, so right here, exponent. That's what we're going to be looking at today. An exponent is a small superscript. Superscript means it's at the top right-hand corner. Here's an example. That little 5 that you see up there at the top right-hand corner of the x is called the exponent. So right here where it says the exponent equals what? Well, that's the 5. That big X you see there is called the base. And most of you guys should know this already. I know you talked about it back in junior high. So X is what we call the base. The exponent is 5. It's the little number on the top right-hand corner. So what does that actually mean? What does x to the 5th power mean? What does it represent? It tells us right here. It's the number of times a symbol or a number is multiplied by itself. So all this means is it means x times x times x times x times x. 1, 2, 3, 4, 5. 5 x's. That's what it means. We're multiplying x by itself 5 different times. Take a look at the next one. Here we have 2 to the 4th power. Which of those numbers would be considered the base? 2. It's the big number. The exponent would be the 4. It's a small number on the top right-hand corner. 4 is called the exponent. Now, what exactly does that mean? What does 2 to the 4th power mean? What does it represent? It means 2 times 2 times 2 times 2. It means we're multiplying 2 by itself 4 different times. So again, base is the big number. The little number on the top right-hand corner is called the exponent. And it represents how many times we multiply the symbol or the number by itself. All right, let's keep going here. There's a couple of rules that we're going to need to be familiar with. It says here, in orders of operations, operations with exponents must be done before multiplication or division and addition and subtraction. Operations with exponents follow their own specific laws. So we got laws of exponents that we're going to be looking at. 2 of these laws are reviewed in the previous activity, which we didn't have a chance to go over. But these are 2 of the rules that we need to know, or laws as they call it. The first one I've highlighted, and I need you to make sure you put a star, circle it, underline it, make sure that it stands out, because we'll be using this rule quite a bit. And that law is the law of zero exponent. Now, what this rule says, or law, is anytime we have 0 as the exponents, the answer would be a 1. That's what this rule says. For any number x, except for a 0, that number to the 0 power is equal to a 1. Let me give you a couple of examples so that you can write them down. 5 to the 0 power. 5 to the 0 power. I tell you what, put that in your calculator. 5 to the 0 power. Now, if you don't know how to put 5 to the 0 power in your calculator, here's how you do it. You type in the 5 first, which we call the base. There is no 0 exponent on your calculator, and there's no button. So you're going to have to use the little button that looks like this right here. It's called the caret symbol. So find that button. Caret symbol. And it's right above the division sign, right here on the back. Once you type this in, it's automatically going to give you a little box to type in your exponent. Put in a 0. And what do you get? 1. So 5 to the 0 power is 1. Do that again. Try another one. Let's do 12 to the 0 power. 12 to the 0 power would be a 1. Any number that I put in there to the 0 power is always going to be a 1. That's what this rule says. The law of 0 exponent means anytime we have an exponent of 0, we're always going to get an answer of 1. So that's a pretty easy rule to remember. Anything to the 0 power is equal to a 1. The next rule, or the next law that we have, is the law of negative exponents. And it says that anytime we have a negative exponent, we need to fix it, because we're not allowed to have negative exponents. And the way we fix it is by rewriting it as 1 over x to the positive exponent. Now, let me give you a couple of examples on this one. Let's say I had x to the negative 4. That's not allowed. That's illegal. It's against the law. We've got to have positive exponents. So what we do to fix this is simply write it as 1 over x to the positive 4 times. What's that? Well, right now we're just talking about the exponents. This is the law of negative exponents. So it's only the exponent that we're looking at that has a negative. But that's a good question. We'll come across that in a little bit. I'll give you another example. Let's try 2 to the negative 3 power. Again, that's against the law. We can't have negative exponents. So what we do to fix this is we simply rewrite this as 1 over 2 to the positive 3 power. So all we're doing is changing the negative exponent to a positive exponent. But in order to do that, we need to write it as 1 over that base and positive exponent. And you'll see why we do that in a minute. It'll make more sense once we look at another rule that we're going to talk about. Right? Just remember, we're not allowed to have negative exponents. That is against the law. Those are 2 rules. Law of zero exponents, law of negative exponents. So again, make sure you have a big star, you circle it, do something, because it's going to get lost within all these other rules that we have. Make sure it sticks out. Let's keep going here. They want us to use our calculator to complete the tables. Everybody get your calculus. And we're going to do this first one here. 2 squared times 2 to the 8th power. Put that in your calculator for me. Let's see what answer we get. 2 squared times 2 to the 8th power. Now remember, to get that 8 there, you're going to have to use that caret symbol again. All right, I think I heard it. What did y'all say? 1,024. Let's do the next. Let's do the same thing. Put it in your calculator. 2 to the 3rd power times 2 to the 7th power. Let's see what number we get this time.
1,024.
Okay. 1024 again. Let's keep going. 2 to the 4th power times 2 to the 6th power.
1024.
1024 again.
1024.
2 to the 5th power times 2 to the 5th power.
1024.
1024 again. And I'm guessing you know what's going to come next, right? 2 to the 10th power would be a 1024. So notice all of these resulted in the same answer. We all got a 1024. So right here on part A, what do you notice about the answers to each problem? They're all 1024. 1024. All of them equal 1024. They're all the same answer. Look at the second part, part B. What did you notice about the bases of each of these exponents? Look at all the bases. They're always a 2. And the base was equal to a 2. That was for every single one of those. What pattern in the exponents do you notice? Did y'all notice any pattern within the exponents? They always equal to 10.
4, 5.
What? They always equal to 10. Look at that first one. 2 plus 8. Notice how that equals to 10. 3 plus 7. Notice how that also equals to 10. 4 plus 6 equals 10. 5 plus 5 equals 10. So right here, what pattern do we notice in our exponents? They add up to 10. They all add up to a 10. This is the pattern we notice. Which is why we keep getting the same answer over and over and over. Because those exponents, they always add up to a. All right, we're on the next page here. Will the pattern work when investigating expanded expressions? Complete the following table and determine if the rule determined for multiplication of exponents is justified. So let's see here. Multiplication with the same base. Here I've got 3 squared times 3 to the 4th power. Now remember, earlier we said 3 squared means 3 times 3. That's what 3 squared is. 3 to the 4th power means 3 times 3 times 3 times 3. If I were to multiply all of these together, what would we get here? 729. Now, look over here. They want us to rewrite the expanded notation as a single base raised to a single power. So in other words, what do you notice about all the bases here on this? They're all what? Threes. So right over here, we're going to use a 3 for our base. Exponents. What I want to do is I'm looking at this expanded form. Notice how many 3's I have here. I've got 1, 2, 3, 4, 5, 6. I'm multiplying that 3 by itself 6 times. So my exponent over here is going to be a 6. So this is the same thing as 3 to the 6th power. Look at another one. 2 to the 6th power. 2 to the 6th power means 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6. 2 to the 7th power means 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Going to multiply those together. Notice they all share the same base, and that base is a 2. Look how many 2's we have here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of them. So this is 2 to the 13th power. Next one, 7 to the 3rd power, which simply means 7 times 7 times 7. That's what 7 to the 3rd power is. 7 to the 5th power means 7 times 7 times 7 times 7 times 7. There's 5 of them. If I were to multiply these two together, notice how all the bases are a 7. And notice if I add up all the 7s, I got 1, 2, 3, 4, 5, 6, 7, 8. 8 of them. Guys, are y'all noticing any kind of a pattern here? Is there any way I can jump from this thing to this thing without having to show all of these 3's here? Same thing here. Go from here to here. What'd you say? Add the exponents. So if we have the same bases, we can take a shortcut without having to do all of this. All we're really doing is taking these 2 exponents and adding them together. So on this next one here, let's see if we can skip all of this work and go straight to the answer. Notice how the base is still going to be a 12. 8. So if I add those 2 exponents, the 2 plus the 3 would now give me a 5. Now isn't that much easier having to skip all that work and just go straight to the answer? Same thing here. X squared times x to the 3rd. We're going to keep that base. Keep the x. The base is still the same. What do I get when I add these 2 exponents together?
5.
5. 2 plus 3 would give me a 5.
What's the last one?
Now that last one, what's the base on the last one?
X.
X. So let's keep that base. Now it's kind of hard to see there, but those exponents, the first exponent is an A, the second exponent is a B. So what did we say we were doing with those 2 exponents? Adding them together. So what do I get when I add an A plus a B? No. Close, not AB, but A plus B. We're adding them together, guys. A plus B, A plus B. What we just found is our next rule here, guys. A says, what does the exponent mean in each of these expressions? What does the exponent mean? Remember, it's the same thing that we said earlier. What's that? All right, that's how many times we're multiplying, okay? The exponent represents how many times we multiply the base. How many times we multiply the base. So we have an exponent of 2. That's how many times we're going to multiply the base. If the exponent was a 5, well, that's how many times we're going to multiply the base. That's what the exponent is. Number 3, write a conjecture or a rule explaining the process of multiplying same bases raised to a power. Write a rule explaining the process of multiplying same bases raised to the power. It's kind of like what you notice here, the shortcut. What do we notice on the shortcut here?
Just add the exponent.
Add the exponents, but we keep the base. All right, that's what we're going to write here. We're going to keep the same base. Keep the same base. And what did you say to do with the exponents? Add the exponents. All right, so let's put that. Add the exponents. So this is what we just found. This was our little shortcut. We don't want to write out all the 3's and all the 2's. That's too much work. So we're going to go straight to the answer. All we need to keep in mind is we'll keep the base, then we'll add up the 2 exponents. That's our little shortcut. That's our rule. That's going to be our conjecture, our law. All right, let's keep going here. Next part is a little bit different. Here. On this one, we have 3 to the 4th power divided by 3 squared. What we're going to do is we're going to expand this. 3 to the 4th power. 3 to the 4th power means 3 times 3 times 3 times 3. There's 4. That's what the exponent is, 4. 3 squared at the bottom there means 3 times 3. Right? Look what happens. Look what's going to happen here. These 3's cancel each other out. Those 3's are also going to cancel each other out. Will these 3's cancel each other out? No. In order to cancel out, you have to have one on top and one on the bottom. One in the numerator, one in the denominator. So I want you to notice what I'm left with. I'm left with 2 3's. 3 times 3, which is the same thing as what? 3 squared. Let's write that right over here. 3 squared. 3 times 3 is 3 squared. Let's do a couple more, and we're going to see if we can't find some kind of a shortcut like we did with multiplying. 2 to the 7th power. 2 times 2 times 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6, 7. I got 7 2's. That's 2 to the 7th power. 2 to the 6th power. 1, 2, 3, 4, 5, 6. Let's come over here and cancel some outs. Those cancel, those cancel, those cancel, those. Look what I'm left with. I'm left with a 2. One time you already found the shortcut. That quick? Don't tell anybody. I want to see if somebody else can figure it out. You told me, but maybe they didn't hear. Let's do one more. Let's give these other guys a chance. 7 to the 8th power. 1, 2, 3, 4, 5, 6, 7, 8. That's 7 to the 8th power. 7 to the 3rd power. There's 7 to the 3rd power. Let's come over here and cancel some out. Notice I still got 7 for my base. How many 7s do I have left over? 1, 2, 3, 4, 5 of them. So 7 to the 5th power. Okay. So now we see we don't have to do all of this work. We can go straight from this thing to this thing. We can go from this thing to this thing over here using our little shortcut. And you said the shortcut was what? Subtracting the exponents. All we're doing is taking the exponents and subtracting. Notice how 4 minus 2 is 2. Notice how 7 minus 6 is 1. And technically there is a 1 right here. You just don't see it. Anytime you have a number, there's an invisible exponent of 1. Notice here we got 8 minus 3. 8 minus 3 is 5. So if I use that rule again, what should I have over here? 12 to the, what, 6 minus 2? 6 minus 2 is
6, 5, 4.
Oh, 4.
4.
Say 4,
Come on, what do you think so much?
You think it's 5?
6 minus 2 is 4. So we have 12 to the 4th power. The next one. We keep the base, keep the x. You said we were going to subtract the exponents. That's an A and that's a B. A minus B. There you go.
A minus B.
A minus B.
What about B minus C?
All right. All right, so A wants to know how does the exponent, or what does the exponent mean in each expression? What does it mean? It represents how many, let's write this down. How many sets of the base are in the expression? How many sets of bases are in the expression? For example, 3 to the 4th power. That 4 meant that's how many 3's we had. 3 squared. The 2 means how many 3's we had. We had 2 of them. How many sets of bases are in the expression? B. Here's where that shortcut comes in. B. Write a conjecture or a rule explaining the process of dividing the same base raised to a power. So what's the rule, the shortcut? Keep the base. Let's keep the same base. Like we did earlier, keep the same base, but this time we're going to subtract the exponents. Now, by the way, guys, when we say we're going to subtract the exponents, remember, it's always going to be the top exponent minus the bottom. So it's 4 minus 2, 7 minus 6, 8 minus 3, 6 minus 2. So it's the top one minus the bottom. So let's not forget, it's got to be in that order. Got to be in that order. All right, so now let's summarize what we've just found out. Here's the laws that we just created. We have the multiplication law. Now, this multiplication law, first of all, in order to use this law, the bases have to be the same, like the examples that we saw a second ago. And if they're the same, then we can add up the exponents, just like that rule that we came up with earlier. Make sure you highlight it, circle it, put a big star by it, but do something because that rule is very important. It's probably one that we're going to use the most often.
What if the bases aren't the same?
Good question. What if the bases are not the same? I like that question. For example, what if we had 2 to the 3rd power times 5 to the 5th power? Could I use that rule or that law on this one? No, because the law says the bases must be the same. So don't try and add exponents if the bases aren't the same. You've got to have the same bases in order to add the exponents. Very good question. All right, so they give us a couple of examples down here at the bottom. First one, 2 squared times 2 to the 3rd power. Let's use our little shortcut here. We're going to keep the base, like we said, and add up the exponents. So 2 plus 3 would give me a 5. Bam, done. That's the answer. 2 to the 5th power. Next one, 4 squared times 4 squared. Keep the base.
4.
Add up the exponents. 4. Next one, x to the 3rd times x to the 5th. Again, we're going to keep the base, keep the x, add the exponents. 3 plus 5 is 8. Now, if we wanted to, guys, we can actually take this a step further, at least the first 2. 2 to the 5th power. I could ask you to actually put that in your calculator and give me the value. Let's go ahead and do that. Go to your calculator and let's find out what is 2 to the 5th power.
32.
32.
32.
What about 4 to the 4th power? We can also put that one in our calculator. That one would be 256. What we cannot put in our calculator
0.
is x to the 8th power. And that's because x is a variable. So we can't put that one in our calculator. All right, so that's the multiplication law of exponents. When you're multiplying, you add the exponents. When you multiply, you add exponents. Now let's take a look at that division one. Now the division is the complete opposite of multiplication. Rather than adding the exponents, we're going to subtract the exponents. But again, keep in mind the bases must be the same. In other words, I cannot come over here and do 5 to the third divided by 6 squared. I cannot subtract those exponents. Those bases are not the same. All right, so let's go ahead and use our little rules down here at the bottom with these examples. 3 to the 10th divided by 3 to the 5th. We'll keep the same base, which in this case is a 3. And we'll subtract the exponent. So 10 minus 5 would give us a 5. There it is. We're done. 3 to the 5th power. Next one. X to the 11th divided by x to the 24th.
13.
Keep the same base. Keep the same base. And subtract the exponents. Now remember, we said it's got to be the top one minus the bottom. 11 minus 24 is negative 13. Very good. Negative 13. Now we have a problem here, guys.
You can't do that one.
That's right. Why?
Bases aren't the same.
No, wait, time out. I'm not looking at C yet. I'm coming back to B over here.
Oh.
We're looking at
So
B.
there's a negative
There's a
ex-
problem.
negative
What's that?
exponent.
Negative. Remember I told you at the very beginning here, it's against the law for us to have a negative exponent. But I told you there was a fix for that. It's one of the very first rules I had you highlight. If we have a negative exponent, we need to fix it. So I'm going to fix this real quick. This is now going to become 1 over x to the positive 13. I cannot have negative exponents. They must be positive. Now I'm good. Now I can move on to the next one. Don't ever leave your answer with negative exponents. If you leave a negative exponent, I'm counting it wrong. All right, now let's go to C. And I think I heard you say something earlier.
That one, the bases aren't the same.
There you go. We cannot do this one because the bases aren't the same. But notice they give us a little hint down at the bottom. Be careful with problem C. How could we rewrite the problem so that the bases are equal? You're right, the bases aren't the same right now. But there is a way we can fix it so that the bases are the same.
Divided by negative 2.
No, not quite.
Right.
No.
Notice this one has a base of 2. But the bottom base is a 4. Not a 1 or 4. I want a 2. So here's what I'm going to do. This 4, I'm going to replace that 4 with a 2 squared.
You don't have to do anything.
Why did I change the 4 to a 2 squared? Well, what is 2 squared?
You divided 4 by 2.
Isn't 2 squared also going to give us a
4.
4? And now won't I have the same base? I've got a 2 here and a 2 here. Now the only thing is, and I wish they hadn't put this in quite yet because there's an other rule that we have. I had a 2 out here to begin with. And I don't like this because it's kind of jumping the gun here. I've got 2 exponents, and these 2 exponents, when I take a look at those 2 exponents, 2 times 2 will give me a 4. And it's a little confusing right now because there's a rule that we haven't discussed that we'll be talking about at a later time that'll describe that. But just go with me for right now. Notice I have the same bases now, so let's keep that base. And now I can subtract the exponents. So 6 minus 4. 6 minus 4 would give us a 6 minus 4?
Oh, 2.
2. So this now becomes 2 squared. Now realize that one right there is probably a little trickier. And that's because they threw in an extra rule that we really haven't covered yet. So don't worry too much, guys, if this one gave you some trouble. Because we'll talk more about that type of problem later on. So don't get too bogged down on that.
That's what I said. I think we're going to switch it.
What's that?
Like I said, just doing 2, 2. I think we're going to switch it to 4. At the beginning.
Up here, we could do that also. As long as the bases are the same, we could do it. The question was, why didn't I change this 2 on the top to a 4? And we could have. And guess what? We would have ended up with the same thing I have over here, 2 squared. We still end up with the same answer. All right, let's keep going here. Now, here's that rule that I was talking about. They kind of jumped in a little too early here. The next rule we have, and it's the last rule that we're going to see today, is called the power law of exponents. Power law of exponents. And that rule is right here highlighted. And it says that x to the a power to the b power is equal to x times a times b. Again, sounds confusing for something that's very simple here. All we're doing is taking these two exponents and multiplying them together. So 2 times 3 would give me a 6. That's all the rule says. Take the two exponents, multiply them together. B, keep the 10.
8.
Multiply those two exponents. 4 times 2 is 8. Same thing over here. Keep the base. Multiply the two exponents. 4 times 5 is 20. That's all this law says. Power of law of exponents says if you have those two exponents, you're going to multiply them together. All right, that takes care of all of our rules. Now what I need